As the last part of this lecture, I now want to talk a little bit about discriminant analysis. I left this bit to the end because it's not such an important analysis. You might find it less frequent in your day-to-day work as a data scientist, but I still think it's important to know about it and to understand the methodology behind it. So it's an alternative method to logistic regression, and as we see, linear discriminant analysis will also give us a linear decision boundary, similarly to logistic regression. So the basic idea behind discriminant analysis is actually quite simple, and I might just explain it in an example, and to be more precise, in the same example we talked about previously. So again, let's just look at the students which passed and failed the exam, depending on the numbers of hours studied, which again is on the horizontal axis, and let's just label them in two colors. So the green ones are the ones which passed, and the red ones are the ones which failed. And what we can do is actually fit a Gaussian distribution to the number of observations. So let's just assume, you can always assume that I sample outcomes from a distribution. So for example, if I had this red Gaussian there, points sampled from this Gaussian will look more or less like the red dots shown, the students which failed, and then the other curve, the green curve, would be more or less the Gaussian representing the students which passed. So how do you obtain those Gaussians from the data? I would just take the mean and the variance. So the center of this curve here, the red one, is given by the mean. I can just get the mean from the data by just summing up all the hours studied by the students which failed, and then dividing by the total number. And similarly for the students which passed, I can also compute the mean, and I will get this value here. Now I can compute the standard deviations also from the data, and in discriminant analysis, the standard deviation is computed from the pooled data, but it doesn't really matter where I get it from. I can calculate the standard deviations separately for each of the two distributions, or I could say, well, I really want a model where both distributions have the same dispersion, and I pool the data to compute the standard deviation. Doesn't really matter which one I do. I will get curves which look like this. So I have the Gaussian for the population of students which failed, and the Gaussian for the population of students which passed. And now if I wanted to make a classification out of it, all I can say, I can classify with regard to the probability which is higher. So for example, on the left I can see that the red curve is above the green one, so the probability of failing is higher, whereas on the right the green curve is above the red one, and the probability of passing is higher. And the decision boundary would thus be exactly here, where the two probabilities are the same. So the green one would be the probability of passing, the red one would be the probability of failing, but rather than modeling it using a sigmod of a linear function, I just model it now by a Gaussian over the population. So I just get from the data the Gaussian which models the population of students which pass, and this will be just my probability of passing there. So the decision boundary would be this line, and everything above I would classify as pass, and everything below I would classify as failed. And you could see the answer is again somewhere around 2.8, similarly what we had before. And this idea also generalizes to higher dimensions, similar as I did for the logistic regression. So if I look at a 2D pictures, again, here I have 2 dimensions here, x1 number of hours studied, and say x2 number of hours slept. And now I can model those Gaussian, which again, this probability is coming out of the plane here. So this is just like some height lines like you do for, if you look at a mountain map, this would just be the one Gaussian would effectively be this mountain here with the top here, and then it's kind of the cupola is here, and the other mountain could be, say, this one here with the height map like this. And then as I had here it's kind of the mountains in a plane, and they intersect here where the same height. Similarly here in the next pictures, the mountains will be this cupulas, the Gaussian bell shapes, and where these 2 bell shapes intersect and have the same value, there's where the decision boundary is, which is this red line here, which is exactly when those bell curves, which are kind of coming out of the plane, have the same value. So this works exactly the same. And interestingly, if I assume the Gaussians to have the same variance, and I will explain in a little bit the math behind it, but if I assume they have the same variance, then those bell shapes will have the same orientation. They will be kind of as equally squeezed and equally oriented. So this kind of squeezing here and the orientation will be the same for both Gaussians. And you can already see by eye a little bit, if they are the same and only the center point of the bell shapes differs, then the intersection line will be a straight line. This is why it's called linear discriminant analysis, because the decision boundary is linear here. So to recap, I will look at all the data, I will fit a Gaussian to each of the classes by just computing the sample mean and sample variance. If I assume the variance are the same, I will get this situation, which is linear discriminant analysis, where my decision boundary is linear. And you can actually see that if I now assume the variance to be different, all which will change is effectively the orientation of those Gaussian bell curves, and then the line will look quadratic, and you can actually show, we will do that in a second, that the decision boundary is a quadratic function, and this is why it's sometimes called quadratic discriminant analysis. So this is a nonlinear model. So this is why it's also nice to introduce the discriminant analysis, because it's a model which is simple and it has a straightforward nonlinear extension. So if you think, I'm building this linear model, but my data somehow is not really linear, I need something with a bit more flexibility, and I want a quadratic relationship, then discriminant analysis is something which very easily generalizes. So here again, I have the 2 Gaussians, one for the students which passed, one for the students which failed. Each one has its center, which would be the mean, but here they have different variances here. And this is why the intersection is quadratic. And I don't want to talk too much about the math, because it might be a bit cumbersome for people who are not so familiar with multivariate Gaussian, but it might be worthwhile writing it down. So it's useful for you to understand that the probability of a Gaussian in one dimension, we already talked about it, but in higher dimensions, it's effectively something which is a exponential of e to the minus a half, and now I have something like x vector minus mu transpose. Then I have this covariance matrix, which takes the role of the normal variance in 1D, and again I have x minus mu vector here. And there's some form of normalization, which is just 1 over whatever square root of the determinant of the covariance matrix. It doesn't really matter, I will just write a normalization which depends on the covariance sigma there, which is 1 over whatever square root 2 pi of determinant of sigma. But it doesn't really matter exactly what it is for our case. So this could be true for any Gaussian. So in the general case, if I have 2 Gaussians, I could have distribution 1 and distribution 2. and they have different, in general, different mean and different covariances. And now, so this Gaussian, as we discussed, it will have this cupola structure here, and we know that the mean here, mu, will be just the center point of the Gaussian. So if here's 0, mu vector will just be this. And as I discussed, the covariance matrix will tell me about the orientation and the squeezing there. So a normal Gaussian will be isotropic. It doesn't change if I rotate around, so there's no squeezing. But depending on the sigma, I will have squeezing in different directions. And effectively, for those of you who like a bit of math, so this sigma matrix here, which is the covariance matrix, it will, you can decompose it using what is known as eigenvalue decomposition into something which is a unitary matrix, a diagonal matrix, and the unitary matrix inverse or transpose. And effectively, lambda is the diagonal matrix which has the so-called eigenvalues in the diagonal. So lambda will just be a diagonal of lambda 1 and lambda 2 in the 2D case, and U is just a vector, a matrix which has the eigenvectors as columns here. So this is the general case, and people who have studied math will probably, or some math in their degree, will probably remember this. And actually, the eigenvectors v1 and v2 will exactly define the orientation. So the orientation of this ellipse here is given by v1 and v2, and the squeezing here, how far it is squeezed in each of the dimension, is given by lambda 1 or lambda 2. I think the inverse to be more precise, but it doesn't really matter. All which matters is that I have two parameters which define or two vectors which are orthogonal and which define a kind of new coordinate system in which I rotate my Gaussian, and then I squeeze it. Or you can think about it the other way around. I squeeze it along the x-axis and I squeeze it differently along the y-axis, and then I rotate it to be aligned with v1 and v2 rather than x and y. But so any arbitrary bell shape is basically obtained by from the normal bell shape, which is just isotropic and centered at 0, by shifting it with mu and then tilting and rotating it. And the tilting and rotating is described by sigma. So this is how a general Gaussian looks like. This is just a recap of a multivariate Gaussian if you can't remember this from kind of the probability class, but some people might not have discussed that in probability class of how you can interpret the sigma. You might have seen the formula, but you might have not seen the interpretation here, which I think is useful because some people don't like formulas. So maybe this kind of inverse sigma doesn't mean much for you, but maybe even eigenvalue doesn't mean anything for you. But if you can kind of associate with the picture, this is probably quite useful. But in any case, so if we go back to our exercise now that we understand what the multivariate Gaussian is, so we basically have two multivariate Gaussian. So there's kind of one here and say one here. So this one has a vector mu2 and this one here has a vector mu1 for the center, and then this one here has some covariance sigma 1 and this one here has a covariance matrix sigma 2, which again in practice you can obtain it from the sample covariance matrix, exactly as you obtain the mean and the sample variance. You can obtain the sample covariance as well using the standard techniques from the data. Now when we want to evaluate the decision boundary, which is this red line here, we are looking for the points where those two probabilities are the same. So effectively I'm looking for where p of x1 p of x, p1 of x is equal to p2 of x basically. there are some other normalization terms floating around if you do the full analysis, but I'm ignoring them because essentially it boils down to this. I want to see the red line, this decision boundary here, which is the line when those two probabilities are the same there. And if I look at the form of those probabilities, so I want this one equation where I is equal to 1 to be equal to the same equation where I is equal to 2. And you can already see, because of the exponential, it's worthwhile to take the logarithm of it. So I will get something like, if I take the logarithm, I get something like the logarithm of my normalization of sigma 1, and then plus the logarithm of the exponential, which is just the exponential, which is minus, and then I get a half x transpose minus mu 1 sigma 1 inverse x minus mu 1, and then this should be equal to log of sigma 2 minus a half x minus mu 2 transpose sigma 2 inverse x minus mu 2. Here we go. Now this is the general kind of equation of when those two lines are the same. So the equation which determines this decision boundary is just this equation here, and you can see those are just constants, like sigma 1, mu 1 are all constants. They are fixed. The only variable here is x. So this is an equation as a function of x, and you can see it has terms which are quadratic. Oh, I forgot to transpose here. Those are terms which are quadratic, linear, and constant. But the equation is at most quadratic. So the generic solution to this equation is quadratic in x. This is why the general decision boundary is quadratic, as I just said, and that's why it's called quadratic discriminant analysis. But if you look at the case where the variances are the same, if both curves have the same variance, then obviously sigma 1 is equal to sigma 2. So in the case where so this sigma 1 is equal to sigma 2, so it's quadratic when, for the general case where sigma 1 is not equal to sigma 2, but for the special case where sigma 1 is equal to sigma 2, then obviously this term will be the same as this term, and it will cancel here. And also in this expansion here, the quadratic term in this expansion will just be x transpose sigma 1 x, and here it will be x transpose sigma 2 inverse x inverse here. Those are the quadratic terms, but if sigma 1 is equal to sigma 2, those will just cancel from both sides. I'm only left, the only different terms are the linear terms, because they depend on mu 1 and mu 2, which are still different there. So now the quadratic terms cancel, and then this equation is just linear, and this is why I will get a linear decision boundary, and then it's called the linear discriminant analysis. So, which was this case here. This is why we have just shown a bit in mathematics that if I model the distribution of each of the student classes by a Gaussian, I assume the Gaussian have different means which are fit from the data, then I will get this case and the decision boundary is exactly linear. If I allow the Gaussians to not just have different means but also different covariances, now the decision boundary can be shown to be quadratic, which is what we just did here, and then I have the quadratic discriminant analysis, like you can see in this picture. So this finishes the discussion about discriminant analysis. You now have this defined. I think it's a very nice and very simple model. You know how it is computed, because you can get the means and covariances straightforwardly from the data, say using the kind of population mean and covariances. And you also know a little bit about the math behind why the one is linear and why the other one has a quadratic decision boundary. And hopefully in doing so, in kind of revising the math, we also kind of recalled a little bit the background around multivariate Gaussians, which is something quite useful in general. Gaussians appear all over the place, and you really want to know a little bit about Gaussian distributions and multivariate Gaussian distributions if you work in data science, because they come up more often than you think. So this is all I wanted to say about discriminant analysis.